Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will discuss questions on waves and Doppler effect from Cambridge AS Physics Paper 2. And this paper is from March 2021. Part A is simply asking us to state the principle of superposition. Principle of superposition simply tells us when two waves meet at a point, how we can find the resultant displacement of resultant wave. Let's try to understand this one a little bit in detail before we write our final answer for this question. You can see here in this figure I have already drawn three different waves. Let's say this wave is wave 1 and this is second wave, and the third one is resultant wave of these two wave. If you look at this point, you can see the displacement of black wave. So this is displacement of black wave. But at the same point, second wave, it also have displacement. Blue wave, this has also displacement. And this is the displacement of blue wave. But if we add these two displacements together, we can find the displacement of resultant wave. Simply, you need to add displacement of these two waves. Now, let's look at this point now. At this point, you can see blue wave, it has negative displacement. So this is displacement of blue wave. But the black wave, it has positive displacement. And this is displacement of black wave. But if we add these two together, one is positive, one is negative, we can find the resultant displacement of resultant wave. And this is resultant displacement of resultant wave. Now, if we look at this point, wave 1 and wave 2, they have zero displacement. So the resultant displacement of resultant wave is also zero. This is what you need to understand about principle of superposition. Now let's try to write down our final answer. So this is how you can state principle of superposition. Simply you can say when two waves meet at a point, the resultant displacement is equal to the sum of individual displacement of each wave. For part B, it is given to us that a transmitter produces microwaves and these microwaves are traveling in air. Air is the medium, very important. And they're moving towards a metal plate. Experimental setup is shown in figure 4.1. We can see here we have microwave transmitter. We also have microwave detector, or simply we can say microwave receiver. Metal plate is also placed at the end. And it is also given to us that the wavelength of these waves is 0.040 meter and stationary waves is formed between transmitter and the plate. Question is simply asking us explain the function of the metal plate. Why do we need metal plate in this case? First thing we need to understand is that stationary wave is a resultant wave of two waves. If there is only one wave, there will be no stationary wave. So it means we need two waves. Means we need one incident wave and one reflected wave. So when those two waves they will meet, they will form stationary wave. So the purpose of this metal plate is to reflect microwaves. So this is very simple how you can answer. If you look at this one, I have already drawn here. So this picture is very clear to see how stationary waves are formed between metal plate and microwave source, or you can say microwave transmitter. Now the function is simply, the function of this metal plate is to reflect microwaves. So this wave is reflected wave. This is reflected wave and this one is incident wave. This one is incident wave. Here is final answer. So this is how you can write down your final answer for this question. For the second part, we need to calculate the frequency of the microwaves, but our answer has to be in gigahertz. Frequency of wave simply is equal to the speed of the wave in the medium divided by wavelength of the wave. In this case, the wavelength of microwaves in air is given, that is equal to 0.040 meters. This is given to us. Now the question is that what is the speed of microwaves in air? We have discussed that all electromagnetic waves, they travel at speed of light in vacuum. So this is speed of electromagnetic waves in vacuum. But the speed of electromagnetic waves in vacuum is almost equal to speed of electromagnetic waves in air. So the speed of electromagnetic waves in air is also equal to 3 times 10 to 8 meters per second. Microwave is also an electromagnetic wave, so its speed is also equal to 3 times 10 to 8 meters per second in air. So simply we can write down here. So the speed of microwave in air is 3 times 10 to 8 meters per second. If we solve this one, our final answer will be 7.5 times 10 to 9. This is answer. But we need to write down our answer in gigahertz. So this is simply 7.5. So our final answer is 7.5 gigahertz. For third part, it is given to us that a microwave receiver is initially placed at position X where it detects an intensity minimum. The receiver is then slowly moved away from X directly towards the plate. Means first of all, detector is placed at this point and this is position X and it detects intensity minimum, means at this point there is node. And then this detector is moved to the right, detects another intensity minimum, or simply you can say node. Node is detected at this point. And question is asking us to find the shortest distance between these two nodes, and the distance between two nodes, it is equal to lambda by 2. So simply we can say distance is lambda by 2, and the value of lambda, that is equal to 0.040 meters. Simply we need to divide this by 2. So this is our final answer for this part. For the second part, we need to determine the number of intensity maxima. It simply means that we need to determine the number of antinodes when the detector is moved from position X to a new position that is 9.1 centimeter away from X. So it simply means that at this point our detector was placed at this position, means at position X. Then we move our detector to the right and the new position from this one is 9.1 centimeter away. We have already discussed that the distance between two nodes, that distance is equal to 0.020 meters, or simply we can say this distance is equal to 2 centimeters. So if we move detector from here to here, so this distance is 2 centimeters. Then if we move to next node, it will cover extra 2 centimeters. If we place at this point, so the distance from X will be equal to 6 centimeters. If we place here, distance between X and this new position is 8 centimeters. In question, we have to move this one by 9.1 centimeters. So it means we have to move up to this point, up to here. Otherwise, simply you can understand, if we move to this one, distance will be 10 centimeters, but we have to move by 9.1 centimeter. So distance between X and the new position here, distance is 9.1 centimeters. Now question is asking us determine the number of intensity maxima. So this is one intensity maxima, so this is 1. So here we have the second one, here we have third one, so this one will be the fourth one, and this one is fifth one. So the total number of intensity maximum detected by detector when the detector is moved from X to new position, that is 9.1 centimeters away from X, is 5. So total number of maxima is equal to 5. For question 5, it is given to us that a source of sound is moving in a circle and the radius of the circle is 2.4 meters. And source of sound is moving at a constant speed in a horizontal circle and the speed of source is given, that is 12 meters per second. And frequency of source is also given, means the frequency of sound produced by source is given, that is 950 hertz. So we can simply say this is fs. In this case, f is equal to 950 hertz. And speed of sound in air is also given to us, and it is also given that observer is at rest. We need to calculate the minimum frequency, and in our answer we need to use three significant figures. First of all, let's try to understand when the frequency is minimum. Frequency is minimum when the source is directly moving away from listener. So here frequency will be minimum, and frequency heard by listener will be maximum when source is moving towards listener, directly towards listener. Directly is very important. When directly moving away, frequency will be minimum. When directly moving towards listener, frequency heard by listener will be maximum. Question is asking us to find the minimum frequency, so we need to simply use Doppler equation when the source is moving away and listener is at rest. So f minimum in this case will be equal to v over v plus vs times frequency of source. Speed of sound is given to us, and this v is also speed of sound, and vs is speed of source that is given, that is equal to 12 meters per second, and frequency of source is 950 hertz. We simply need to solve this one to find the minimum frequency observed by this listener. In this case, our answer is 917.6 hertz. But the question is asking us, we need to write our answer using three significant figures, means our answer must have three significant figures. So we can write down our answer 918 hertz. So this is our final answer, and it has three significant figures. For part B, question is asking us to calculate the shortest time interval between minimum and maximum frequency observed by listener. For this question, it is given to us that the source is moving in a circle and radius of circle is 2.4 meters, and the speed of source is also given, that was given in part A, and the speed of source is 12 meters per second, and the source is moving at a constant speed. Let's try to understand when the frequency is minimum. Frequency is minimum when the source is directly moving away from listener, so we can say frequency will be minimum at this point, and frequency will be maximum when the source is moving directly towards listener. You can also look at this diagram. When the source is moving away, in this case directly away, frequency will be minimum, and when the source is moving directly towards observer, means towards listener, frequency will be maximum. Now if we can find the shortest distance between these 2 points, then we can simply divide by velocity, mean the speed of source, and we can find the shortest time interval. First of all, let's try to find out shortest distance, mean the shortest distance between 2 points, and the shortest distance is simply equal to 2 pi r divided by 2, or simply we can say this is 3.142 multiplied by the radius. Radius is 2.4. We need to find shortest time, means the minimum time, that will be equal to minimum distance between 2 points, mean between this point and this point. So this is the minimum distance, and we need to divide by the speed of source. So if we solve this one, our final answer is 0.63 second. Welcome to A-Level and AP Physics. In today's lesson, we will discuss question number 4 from May June 2021, paper 2-1. This question is about waves, especially based on properties of waves and diffraction grating. These two concepts are very important because most of the time they will ask about these concepts in CIE exam. For part A, we need to state what is meant by wavelength for progressive wave. First of all, let's try to understand what is progressive wave. Progressive wave is also called traveling wave because these waves transfer energy in direction of wave. So that's the reason we call them progressive waves. And examples of progressive waves are transverse waves and longitudinal waves. Let's try to understand what is meant by wavelength with the example of transverse wave. So this is an example of transverse wave. Now, if we look at this transverse wave, we can take 2 points. Let's say we take this point and this point. Particles at these 2 points, they will always oscillate in phase. So simply we can say these 2 points on the wave, they are in phase, and the minimum distance between these 2 points is equal to 1 lambda, mean is equal to wavelength. We can also take any other 2 points which are in phase. Let's say if we take these 2 points, so the particles at these 2 points, they will always oscillate in phase. So the minimum distance between these 2 points, this is equal to 1 wavelength. We can also take any other 2 points. Let's say if we take this point on the wave and we take this point, so particles at these 2 points, they will also oscillate in phase. So the minimum distance between these 2 points is also equal to 1 lambda. This is how we can define wavelength. This is how you can write down your proper answer for this question. So let me highlight some points. When you define wavelength by saying the distance between two wavefronts, you must say minimum distance because this is the minimum distance between two wavefronts, or we can say between two crests. We can also say the minimum distance between two crests. We can also say the minimum distance between two troughs, or we can say between 2 points in phase on the wave. Another way to define wavelength is distance moved by wavefront during one cycle of source. It simply means that one cycle is completed by source, the distance traveled by the wave, that will be equal to 1 wavelength. So this is another way to define wavelength. For part D, it is given to us a light wave from a laser as a wavelength of 460 nanometers in vacuum. We need to calculate the period of the wave. First thing we need to understand is a light wave. So light waves are electromagnetic waves. So simply we can say light wave is electromagnetic wave. Now it is given to us, the medium is given. Medium is vacuum, and in vacuum or in air, the speed of electromagnetic waves, this is equal to speed of light, and the magnitude is equal to 3.0 times 10 to 8 meters per second. Means all electromagnetic waves, the speed is the same in vacuum, or we can say the speed is approximately same in air. So V is equal to 3.0 times 10 to 8 meters per second, and this is the speed of all electromagnetic waves in vacuum. Now we have speed and we have lambda. So we can simply say V is equal to lambda times F. F is the frequency, and the frequency is equal to 1 over T. So simply we can say V is equal to lambda over T, or simply you can say multiplied with 1 over T. And from here we can rearrange. So the T time period, this will be equal to lambda over V. Lambda is given to us, and this is equal to 460 nanometers. It simply means 10 to negative 9 divided by the speed of light. So 3 times 10 to 8. Now if we simply solve this, our final answer will be 1.5 times 10 to negative 15 seconds, and this is our final answer. So this is simply we can write down, this is our final answer. This question has 3 marks. The first mark is if you have written this expression, you will get first C mark. And the second C mark is if we have written, means we have plugged in these values. And the last mark is answer mark, and this is A1. So this is final answer mark. If your answer is right, you will get full marks. For part C, it is given to us the light from the laser is incident normally on a diffraction grating. We need to describe the diffraction of the light waves at the grating. So here is diffraction grating. So this one is diffraction grating. In this diffraction grating, you can see small holes, and these holes we call them slits. So these are slits. If you look at light waves, when they pass through this slit, these light waves, they spread out, and this spreading out of light waves as they pass through slits is called diffraction. So simply we need to say that waves spread out as they pass through the slit, and that is diffraction. Let me show you how you can write a proper answer for this question. So this is how you need to write down your answer. If you have mentioned in your answer waves spread out, you will get 1 mark, and this is B mark, means it has to be in your answer. And the second mark you will get if you have mentioned as they pass through the slits, so you will get second B mark. So this question has 2 marks. If you have mentioned waves spread out, you will get 1 mark. The second mark, if you have mentioned as they pass through the slits, you will get second mark. So total marks for this question are 2 marks. Geometric shadow. Maybe some of you are a little curious about that. What is meant by geometric shadow? Geometric shadow means that if these waves, they don't spread, you will not see the light here. So there will be shadow, means no light here. But in this case, when the light pass through the slit, it's spread out. So waves spread into geometric shadows. It means they will illuminate these regions, and these regions are the geometric shadows. For part D, it is given to us a diffraction grating is used with different wavelengths of visible light. The angle theta of the fourth order maximum is measured for each wavelength, as you can see in this figure 4.1. On y-axis, sine theta is plotted, and on x-axis, lambda is plotted. It is also given to us the gradient of this graph. This is equal to g. So from here, simply we can write down the g is equal to sine of theta divided by lambda. So this is the gradient. We need to determine an expression in terms of capital G for the distance d. So first you can start from here. For diffraction grating, we simply understand d sine of theta, this is equal to n lambda. We need to find d. So simply we can write down d is equal to n lambda over sine of theta. If we look at g, this is equal to sine theta over lambda. If we write down 1 over g, this will be equal to lambda over sine theta. Now we can simply replace lambda over sine theta with 1 over g. So this is 1 over g. In this question, it is given to us for fourth order maxima. Fourth order means 4, n is equal to 4, and this is divided by g. So d simply is equal to 4 over g, and this is our answer for this question. We can say d is equal to 4 over g. This question has 2 marks. The first mark you will get if you have written this equation. So you will get first mark, and this one is C1 mark. And the final mark is answer mark. So this is answer mark. For second part on figure 4.1, we need to sketch a graph to show the results that would be obtained for the second order maxima. So this is quite straightforward question. If we look at our previous result, we have found d is equal to n over capital G. For the fourth order, d was equal to 4 over capital G. Now from here, if we rearrange, we can find g. So g will be equal to 4 divided by d. Now question is asking us for second order. So we can write down g for the second order. This will be equal to 2 divided by d. But in this case, we are using the same diffraction grating. So it means d is the same. So d is the same, mean the slit separation is the same for the same diffraction grating. If this become half, now this become half if we compare with 4. So this decreases, this become half. So it means g also become half. Next thing we need to understand, g is equal to the change in y divided by the change in x. So if we draw the line from here to here, delta x is the same. Change in delta x is the same. So if g become half, it means delta y has to be half. So based on this, we can draw the line. So the best way to draw this one is, first we can look at this. So this is about 1, 2, 3, 4, 5 units. So we can take the half of that. So this is about 2.5 units here. And this is 10. So we can take the 5. So this is 1, 2, 3, 4, 5. So 5 units here. And then we simply need to connect. So in this case, delta y will be half, but delta x will be the same. So let me show you how you can draw a proper line. So this is how you need to draw the proper line. So this is how you can draw the proper line. You can see this is about 2.5 here. So this is about 2.5 units, and this is about 5 units. So you can see 1, 2, 3, 4, 5. So this is 5 units. So the gradient of this red line is half, and this question has 2 marks. So if you have drawn in a proper way, you will get 2 marks. So the first mark is for the straight line. If you have drawn the straight line from 400 nanometers to 700 nanometers, you will get 1 mark. If the gradient of this line is smaller than the gradient of previous line, you will get the second mark. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will discuss a typical question on Young's double slit experiment from Cambridge AS Physics. Part A is simply asking us, we need to state by reference to two waves the principle of superposition. Principle of superposition simply tells us when two waves meet at a point, how we can find the resultant displacement of resultant wave. Let's try to understand this one with this simple example. As you can see here, in this case we have two waves. One wave is blue wave, let's say this is wave B, and we have a green wave, let's say this is wave A. As these two waves meet at this point, if you need to find the resultant displacement of resultant wave of these two waves, simply you need to add the displacement of these waves. But we have to be clear about displacement. Displacement is a vector quantity, so it can be positive, it can be negative. So for this purpose, you have to be careful. Let's say the displacement of wave A at this point is dA, and the displacement of wave B, let's say at this point, is dB. If we need to find the displacement of resultant wave, simply we need to add these two, so that will be equal to dr, means the displacement of resultant wave. But if you look at the displacement of these two waves, they have the same displacement and positive, so simply we can say dr is also equal to 2 times of dA, or we can say this is 2 times of dB. Now let's try to understand when these two waves have negative displacements. So if we look at this point, these two waves, they have negative displacements, so we can say the displacement of wave A, this is minus dA, and the displacement of wave B, this is also negative dB. So the resultant displacement of resultant wave, that also will be negative, so this is equal to the sum of these two displacements. So this is displacement of resultant wave. At this point, resultant displacement of resultant wave was this. Let's try to look at one point when one wave has positive displacement and other wave has negative displacement. If we look at this point now, you can see wave B, means the blue wave dB, this has positive displacement, and the green wave, this has negative displacement. So we can say dA1 is positive, dA is negative. But in this case, dB is greater, so the displacement of resultant wave, that will be positive. So this is all about principle principle of superposition is simply you have to add individual displacements to find the resultant displacement. Let me explain to you how to define now. So this is how you can write principle of superposition. Means when two waves meet at a point, resultant displacement is the sum of the individual displacement of each wave. Second part is simply asking us what is meant by coherence. Coherence simply means that constant phase difference. If two waves they have constant phase difference, we can say those two waves are coherent. Constant phase difference. And also we need to understand constant phase difference is only possible if waves have same frequency. Otherwise constant phase difference is not possible. So when we say waves are coherent, it means they have the constant phase difference and also they have the same frequency. Let's try to understand what exactly it means by constant phase difference. As you can see here, I have already drawn two waves. Let's say this wave is wave A and this wave is wave B. Now we need to check these waves are coherent or not. For that purpose we need to check the phase difference. So we can check phase difference at different positions or at different points. If that is the same, it means waves are coherent. If that is not same, it means waves are not coherent. Let's look at wave A at this point. So simply you can see at this given position, these two waves, they're antiphase. So the phase difference is equal to 180 degrees. Now let's check another point now. If we look at this point now, let's say look at this position now. Again you can see these two waves, they have a phase difference that is equal to 180 degrees. This one we can check at any point. If that is constant, then we will say these two waves are coherent. Now if we check at this point and this point, phase difference, again this is equal to 180 degrees. So you can see these two waves, they have a constant phase difference. So it's simply you can say that these two waves are coherent. So this is how you can write your answer. Constant phase difference between the two waves. And constant phase difference is only possible if waves have same frequency. For part B, it is given to us that two coherent waves P and Q, they meet at a point in phase. And amplitude of wave P is given, that is 1.5 centimeters, and its intensity is I. The resultant intensity at the point is given, that is equal to 3 times I. We need to calculate the amplitude of wave Q. First of all, let's try to write down what is given. For this question, it is given to us that amplitude of wave P, this is equal to 1.5 centimeters, and intensity of wave P, this is equal to I. And intensity of resultant wave, let's say, is IR, and this is equal to 3 times I. But by principle of superposition, we also understand that amplitude of resultant wave will be equal to amplitude of wave P plus amplitude of wave Q. So this is what is given to us. Now let's try to understand how we can use the relationship between intensity and amplitude to calculate amplitude of wave Q. We understand for waves intensity is directly proportional to amplitude square, or we can simply say intensity is equal to some constant times a square, or we can simply write down intensity over amplitude square is equal to K mean is equal to constant. This is very important point we need to understand. It simply tells us for any wave, the intensity, the ratio between intensity and amplitude square is constant. In other words, we can also say that I1 over A1 square, this is equal to I2 over A2 square. Now in this case, our I1 is wave P. So this is amplitude of wave p square, and resultant wave in this case is intensity of resultant wave is IR, and the amplitude of resultant wave, that is AR square. So it means the ratio between intensity and amplitude square is constant for any wave. Means that is constant for individual wave, and that is also constant for resultant wave. Now in this case we need to find the amplitude of wave q. We can a little bit rearrange this one, so we can write down, as we need to find the amplitude of wave q, we can rearrange this one again. We can say this is AP, AQ square, this is equal to intensity of resultant wave multiply by amplitude of wave p square divided by intensity of wave p. As the amplitude of wave p is given, we can write down its magnitude plus this is amplitude of wave q. And intensity of resultant wave is given, we can also write down its magnitude. So this is intensity of resultant wave. Amplitude of wave p is given, that is 1.5, and the intensity of wave p is given, that is I. Now simply what we need to do is, if you look at I, you can see in numerator I is here and I is here, we can just cancel out, and remaining what we left is that little bit messy. Let me write down in a clear way. So we left with 1.5 plus AQ square, this is equal to 3 times 1.5 square. Now if we take square root on both sides, we can write down this is 1.5 plus AQ, and this is equal to root of 3 times 1.5. Now if we solve for AQ, we will get AQ is equal to 1.1 centimeters, because we are using unit for amplitude centimeters. So our final answer is 1.1 centimeters. So this is how we can answer this type of question. Part C is all about Young's double slit experiment, and for this experiment wavelength of light is given, slit separation is given, that is A, and the distance between screen and double slit is given, that is capital D, and fringe spacing is also given, that is X. So let me explain to you what exactly is fringe spacing. Fringe spacing is the distance between two adjacent bright fringes. In this case, this is X, and X is called fringe spacing. And it is also given to us that as capital D is increasing, X is also increasing. And question is asking us, we need to find the slit separation A. But in this figure, you can see as D is increasing, X is also increasing, mean the spacing between bright fringes, means this value of X is also increasing. And question is asking us, we need to find the slit separation. In order to find slit separation, we need to understand the relationship between slit separation, fringe spacing, wavelength of light, and the distance between slit and screen. So this is the relationship. From here, as we need to find A, we can just rearrange this. Now the value of wavelength is already given to us, and that value is 680 nanometers. So we need to multiply with 10 to negative 9. But value of D and X is not given. So we can just pick any point on this line and we can plug in value of X and value of D. But I will take this point because this is more easy to find value at this point, the coordinates of this point. So in this case, the value of X is given. X is 4 millimeters. This is value of X, and we can also find the value of D, that is 2 meters. Now simply we need to solve this one, and if we plug in values in calculator and we solve for A, our final answer will be 3.4 times 10 to negative 4 meters, and this is value of A, and this is constant. For second part, it is given to us that the laser is now replaced by another laser that emits light of a shorter wavelength. It simply means that this laser now we replace with another laser, and the wavelength of new laser, this is shorter than 680 nanometers. But we are using the same double slit, so A is constant, so A is the same. So simply we can say A is constant. And question is asking us to sketch on figure 5.2 a possible line. So how we can answer this question? This is quite straightforward one if we understand Young's double slit experiment. For Young's double slit experiment, the formula, we need to understand the equation for Young's double slit experiment. And we have used that equation in part A as well. So let me rewrite this one so you can get better understanding. So this is what we have used for part 1. Now for this part, it is given to us that A is constant. We are not changing A. We are not changing slit separation, but we have decreased lambda. So if lambda has decreased, it means the ratio between D over X. The ratio between D and X, this has to increase. Or simply we can say that the ratio between X over D, this has to decrease. Or we can simply say the gradient of new line has to be shallow, has to be smaller. So the gradient of new line has to be shallow. So simply we need to draw a line below this line. This is how you can draw the line. Welcome to A-Level and AP Physics. In today's lesson, we will discuss an important past paper question on waves and Doppler effect from October-November 2021, paper 2, variant 1. I said this question is very important because this question will help you to improve your conceptual understanding of Doppler effect. For part A, we need to state what is meant by a longitudinal wave. And in our answer, we have to mention direction of transfer of energy. The best example, or simply I can say the simplest example of longitudinal waves is sound. Sound waves are longitudinal waves. Now let's imagine that the wave is moving to the right, means the energy is transferred to the right, or you can say direction of wave is to the right. So simply we can say this is direction of energy transfer. Direction of energy transfer means the wave is moving to the right. Now we need to consider oscillations of medium particles. So if I take one medium particle, let's say this is one medium particle. And so how this medium particle will oscillate? So this medium particle will oscillate to the right and it will oscillate to the left. So this is how medium particle will be oscillating. From here simply we can say the oscillations and energy transfer, they are parallel. So this is what you need to write down. So these are oscillations. So oscillations and energy transfer, they are parallel to each other. And that's all what you need to write down for this question. So now let me show you how you can write down the answer. This is how you can write down answer. Simply you can say oscillations of particles, medium particles, they are parallel to direction of energy transfer. If you write this one, you will get 1 mark. For part B, it is given to us a vehicle travels at a constant speed around wide circular track. It continuously produces sound and the frequency of the sound is 1.2 kilohertz. There is an observer who is standing at a large distance away from the track. And this is shown in figure 4.1. So here is figure 4.1. In this figure, you can see this is the vehicle and this is traveling around circular track. An observer is standing somewhere here. Figure 4.2 shows the variation with time of the frequency f detected by the observer. It is also given to us the time taken for the vehicle to travel once, means to complete one cycle. That time is equal to capital T. So simply you can see from here, so capital T is the time taken by vehicle to complete one cycle, and 2T is the time taken to complete two cycles, and 3T is the time taken for vehicle to complete 3 cycles. On y-axis, this is the observed frequency. So simply we can say this is the frequency observed by observer. So this is observed frequency. Now for part B1, we need to explain why the frequency of the sound detected by the observer is sometimes above and sometimes below 1.2 kilohertz. And 1.2 kilohertz is the frequency of the sound produced by source. Observed frequency, it is given to us, it is sometimes higher than the frequency of the sound produced by source. It is also given to us sometimes observed frequency. This is lower than frequency of the sound produced by source. Now we need to understand why sometimes it is lower and why sometimes it is higher. And that is only possible if there is a relative motion between source and observer. Means there is relative motion between source and observer. So this is the first point we need to understand. Next, we need to understand when the observed frequency is higher than the frequency of the sound produced by a source. Observed frequency will be higher than frequency of the sound produced by source when the source is approaching observer. In this case, our assumption is that observer is not moving. So when the source is approaching, observed frequency will be higher than the frequency of sound produced by source. And the second, observed frequency will be lower than frequency of the source when the source is moving away from observer. So when the source is moving away. And this is due to Doppler effect. Now you see, if you look at this question has 2 marks. So it's asking you to explain why. So one thing you can explain, when there is a relative motion between source and observer, we will perceive observed frequency higher or lower than the frequency of the sound produced by source. Next, you need to explain when it will be higher if the source is approaching, and it will be lower when the source is moving away from observer. So these 2 points simply you have to write down to get 2 marks. And the next part is asking you state the name of the phenomenon in part B1, and that is simply Doppler effect. So if you write down Doppler effect here, you will get 1 mark. So now let's try to understand how we can write down the answer for this question. So this is how you can write down the answer. This is all what you need to write down. I have mentioned all these points here. Frequency varies as vehicle moves relative to stationary observer, means when there is a relative motion, and frequency is higher than the frequency of the source when the source is moving towards observer, and when the source is moving away, observed frequency is lower than the frequency of the sound produced by source. So if you write down these points, you will get 2 marks. And the next one is a B mark. Simply you need to write down Doppler effect and you will get 1 mark. I hope it is clear to you now. For third part on figure 4.1, we need to mark with a letter X the position of the vehicle when it emitted the sound that is detected at time t. So we need to go back to figure 4.2. If you look at figure 4.2, so this is the time, and at this point the observed frequency, so this is observed frequency on y-axis. Observed frequency is maximum, and this is greater than frequency of the sound produced by source. So first thing we need to write down here that observed frequency, this is greater than frequency of the source, and observed frequency, this is maximum. And so this one is maximum. So if the observed frequency is maximum and this is greater than the frequency of the source produced, it simply means that the source is moving towards observer directly, moving towards observer and directly moving towards observer, because this is maximum. So that's the reason we have to mark X here. So vehicle is at this point at time t. Now let's move on to next one. On figure 4.1, mark with the letter Y the position of the vehicle when it emitted the sound that is detected at time 9t/4. Now if you look at this one, this is t/4, so this is 1t/4. So this will be t/2 means 2t/4, and here 3t/4. So here we will have 4t/4, and here we will have 5t/4, here we will have 6t/4, here we will have 7t/4, here we will have 8t/4, and here we will have 9t/4. Now if you look at this point, at this time, the frequency, observed frequency, this is equal to frequency of the sound produced by source. So simply we can say at this time observed frequency is equal to the frequency of the sound produced by source. Now question is asking us to mark that position. So that is possible when the vehicle is here. So in this case you can see if you combine source and observer by this line, you can see the angle between them is 90 degrees. It simply means that there is no relative motion between source and observer. So simply we can write down here no relative motion. And so there is no relative motion between source and observer. So it means vehicle is at this point. Vehicle is at this point. You can also understand why this is not. If you look at this point, for example, so you can also join this one. You see, when the vehicle is moving this way, the angle between source and observer is also 90 degrees, and there is no relative motion. So at this point, observed frequency, this also will be equal to frequency of the source. So here is also no relative motion. Observed frequency is equal to frequency of the sound produced by source. Now, why is this point? If you look at this now, after 1t, so after 1t, the source is here. After 2t, source is again at this point. So you see after 2t, source is here. It means the vehicle is here. So after t/4, vehicle will be here, not here. So that's the reason you have to mark Y here. And this one has B mark, 1 mark. If you have marked X here, you will get 1 mark. And this also has 1 B mark. If you write down simply Y here, you will get the second B mark. For part C, it is given to us the speed of the sound in air is 320 meters per second. We need to use figure 4.2 to determine the speed of the vehicle in B. So simply question is asking us what is speed of this vehicle. For that purpose, we have to use Doppler effect equation. And Doppler effect equation is given in your formula list if you didn't remember. So Doppler effect equation, simply in the formula list, it will be given like this: V over V plus minus Vs. Vs is the speed of source, and here this is the frequency of the sound produced by source. In this question, we need to calculate Vs. So we have two options. We can take minimum frequency, or we can take the maximum frequency. Means when the source is approaching or when the source is moving away. I will take when the source is approaching. So I will be using F naught is equal to V over V minus Vs. When the source is approaching, I will be using V minus Vs, Fs. So this is the frequency of the sound produced by source. Now simply we need to understand when the frequency is maximum. Frequency is maximum when the source is directly approaching, and that value we have F observe is equal to 1.4 kilohertz. So we can simply write on 1.4 kilohertz. And frequency of the source is given in the question, that was equal to 1.2 kilohertz. You can also read from here. So this is 1.2. So this is 1.2 kilohertz. Speed of sound is given, that is equal to 320 meters per second. Now simply we need to plug in values and we can calculate Vs. So let me plug in these values. So F naught, we have this is equal to 1.4 kilohertz. So this is F naught, and the V is speed of sound, and this is divided by speed of sound minus speed of vehicle. This is what we need to find out, and this is multiplied with frequency of source, and frequency of the source is 1.2 times 10 to 3. And now simply we can find out Vs from here. Vs will be equal to 46 meters per second. So this is our final answer. This question has 3 marks. So here you can see this question has 3 marks. The first mark you will get if you have written this one. You are using the maximum observed frequency or minimum observed frequency, you will get 1 mark. And the second mark is that if you are using this right Doppler effect equation when the source is approaching or when the source is moving away, you will get the second C mark. And the final mark is answer mark. You will get this mark if you got the right answer. Now let me help you a little bit how to rearrange this formula. So maybe some students, they're not clear how to rearrange. So let me a little bit help you with this formula, how to rearrange to get Vs. The simple way to do this one is you can multiply here. So F naught here, we can multiply, cross multiply. So you will get F naught times V minus Vs. And this will be equal to V times Fs. Now we need Vs. So we can divide by F naught on both sides. Means you can divide by F naught here. So you will also divide by F naught here. So we can cancel this one here. So we left with V minus Vs. And this will be equal to V times Fs divided by F naught. We need Vs now. So if we move this Vs, so let me write down here. So V minus Vs, so you can add Vs here. So you have to add Vs on other side as well. So this is Vfs divided by F naught. So we have Vs here. So you can see Vs plus minus we can cancel. Now we have Vs here, but this is Vfs F naught is here. We can move this one to the left. So what I'm saying is that V minus, and here you have Vf naught Fs, this is divided by F naught. You can minus Vfs over F naught here. So you also have to minus here. So you will write down Vfs divided by F naught here, and plus Vs we have already here. Now you can see this is negative, this positive cancels. So the Vs finally will be equal to V, this is the speed of sound, minus speed of sound times frequency of the source, means the frequency of sound produced by source divided by observed frequency. So in this formula you can plug in values if you don't know how to calculate from here. So you can just simply plug in values in this one.